In an ideal world, our sample would be all eligible participants for a study. Unfortunately, research costs money, and the more participants you have, the more it usually costs. Therefore, we have to balance the available resources with the needs of our work. Good research involves planning, however, and before you start, you need to know how many participants are required to produce results that are valid and reproducible. You need to know how your study's sample size affects its power. That's the topic of this module in Analysis and Reporting. Remember that most research is about rejecting a null hypothesis. You want to make sure of two things. First, that if you find a significant result, you believe it's not by chance alone. And second, that if you find a null result, it's not incorrect. You need to do a power calculation and figure out a sample size calculation to know how sure you are that these things are true. There are a number of factors that can affect the size of the sample you need. All of them need to be considered when designing your research and your analysis. First, there's the variability in the response you're measuring. You know how much of a change you'd like to see in an experiment, but hopefully, if you've done some pilot work, you have some expectation of the response you think you're likely to see. In addition to that point estimate though, you need to know an expected range of responses as well. If there's little range in responses, then your sample size can be smaller. But if the test you're using has a wide variability, then you'll likely need a larger sample size. Often, the variability is represented by a standard deviation or some other metric. You need to know this factor for a proper sample size calculation. Another factor is the clinical effect you expect to see. Let's say you're measuring mice for weight gain. We need more mice or a larger sample size if we believe that we're going to see a difference of 1 kilogram than if we believe we're going to see a difference of 100 grams. The same goes in human research. Let's say that we're testing some scale of attentiveness in children. If we had a 100-point scale that measures attentiveness, and we believe we're going to see a difference of 10, we need a smaller sample size than if we believe we're going to see a difference of 3. Our study designs will also affect sample size. Proper use of blocking, which helps us to decrease controllable variation in studies, can lead to smaller sample sizes. Our choice in significance levels will also influence sample size. There are generally two types of errors that go into such calculations. The first is type 1 error, or the chance that the significant result we find is actually incorrect. It's the chance that we reject the null hypothesis when the null hypothesis is actually correct. That would be a false positive finding. Many people set the type 1 error at 0.05 or 5%. Some are more lenient and will accept 10%. Some are stricter and set it at 1%. There's no right answer, and you need to decide for yourself. But you need to be clear about it, and you need to know that the lower the type 1 error rate that's acceptable, the larger your sample size will need to be. The other consideration of error is type 2 error. Type 2 error is when a negative result, or a confirmation of the null hypothesis, is incorrect. It's a false negative. It's also equal to 1 minus the power. Most health studies usually accept a power of 80%, although some will go higher and some will go lower. This means that we'd be 80% sure that if we get a negative result, we should believe it. There's a 20% chance of a type 2 error. Other analytical considerations will affect sample size too. If our hypothesis is two-sided, then we need a larger sample size than if it's one-sided. What does that mean? If we're testing a weight loss intervention and only consider the hypothesis that participants in the intervention group could lose more weight than those receiving placebo, it's one-sided. If we also consider whether they lose or gain weight, as opposed to remaining unchanged, then it's two-sided. Two-sided hypothesis testing requires a larger sample, but it's usually the right way to go. Assuming that your intervention can only go in one direction may save you some on the sample size, but it leaves you exposed to incorrect interpretations. Sometimes, however, you're simply constrained in terms of your sample size. You can only have so many participants because the disease is rare, or you have only so much money. In that case, you'll spend less time calculating your sample size and more time figuring out your study's power based on the sample size you have. Sample size and power are interrelated, and setting one will allow you to determine the other. I can't stress this enough. You need to do this ahead of time. You need to know that your positive results are valid and that your negative results can be trusted. You also can't change your mind once you see the final results. We're biased then. That's a problem. We want our research to be reproducible, and knowing that you have adequate sample size and power are important steps on that path. This training module is part of a series funded by the National Institutes of Health.